So, welcome back to lectures on engineering mathematics 2, and this is lecture number 26 on polynomial interpolation, a very important topic in numerical analysis. And in this lecture we will be talking about what is actually the polynomial interpolation, and then we will be also talking about the existence and the uniqueness of such polynomial interpolation. And finally, we will derive a formula which will provide us the error in such a interpolating polynomial. So, coming to the interpolation, it is a process of estimating values between known data points or approximating complicated functions by simple polynomials or determining a polynomial that fits a set of given data points. So, it is a various ways one can define the interpolation. So, the applications, they are like constructing the function when it is not given explicitly, only the values of the functions are given. So, we will construct a polynomial which passes through or fit the given data points. So, that is one of the major applications of this interpolation. The second one, that replacing the complicated functions by interpolating simple functions, and usually these simple functions we take polynomials, because polynomials are really simple functions, because many operations on these polynomials such as the determination of roots, differentiation, integration and many other operations can be performed easily. So, given a complicated function, we will approximate it by some polynomial of some degree, and then we can approximate basically the roots, or we can do the differentiation, integration, etc. Such operations can be performed. So, what is the fundamental principle behind this polynomial interpolation? That will be clear from this Weierstrass approximation theorem, which says that suppose this f is defined and it is continuous on some interval, then for each epsilon, however small, for each epsilon there exists a polynomial p x with the property that f x minus p x is less than epsilon. So, this relation tells that given f x here, a continuous function on a b, we can have a polynomial which will approximate this function with as good accuracy as we want, because epsilon we can fix and it can be very small, and then we can find a polynomial p x corresponding to this given continuous function f x. So, that is the base of this interpolation, or having a polynomial approximation of a given function, because this theorem says that for any given function which is continuous, we can find a polynomial with as good accuracy as we want. And based on this Weierstrass approximation theorem, then we will derive the polynomials corresponding to a given function. So, but the question is that why not Taylor's polynomial, because we have already studied Taylor's polynomial, which was also used for approximating a given function, and now we are talking about some other polynomial with not exactly the Taylor's polynomial. So, the question is that why not just the Taylor's approximation or the Taylor's polynomial, because they are also doing the same job. Given a function, we are approximating a function in terms of the polynomial, which is in this case a Taylor's polynomial. So, let us just demonstrate through this example, and then we will give the reason that why not Taylor's polynomial. We are talking about some other kind of polynomials here. So, constructing the Taylor's polynomial, for instance, this e power x, the exponential function around this x equal to 0. So, the first polynomial of this degree 0, that is a constant function, that is 1, because that is just the function value there. So, f 0 e power 0 is 1, and if we plot this, so this was the exponential function here, and this is this constant function. So, it is having a very good accuracy at this point, or naturally it is matching with the function itself at x equal to 0. Other than that point, the accuracy is not as good, and it is actually getting worse when we are going far away from this point. So, the accuracy is more or less concentrated around this point of expansion, that is the one point here we should note. If we go ahead and we construct this polynomial of degree 1, so that will be 1 plus x, that is a Taylor's polynomial here. And if we plot this, now it is a linear function 1 plus x, and that is given here. And now we have higher degree polynomial, and then we are getting better approximation in the neighborhood again of that point, but if we go far, again this approximation is not at all good. If we construct further, for example, second order polynomial or the third order polynomial, so we plot here the third order polynomial for instance. Now, we are matching quite a bit in a larger neighborhood around this point x equal to 0, and similarly if we continue and construct for instance this fifth order polynomial, then we do see here the accuracy is now in a much wider interval. So, what is the point now here? I mean, the question is that why not this Taylor's polynomial? We have the Taylor's polynomial here, which is approximating the given function, for instance the exponential function. So, the main issues here are the Taylor polynomials agrees as closely as possible with a given function at a specific point, which was the point of expansion, or basically in other words we say that they concentrate their accuracy near that point. So, as we are going far away from that point, the accuracy is not at all good, but in the close neighborhood of that point the accuracy is very good. The second point here, to construct the Taylor's polynomial, we do need information of that function at x equal to 0. So, we need the function value at that point, we need its derivative, second derivative, third derivative and so on, depending on what degree polynomial we want to construct. Whereas, in the interpolation we will again be constructing polynomials, but there we need the function value at different points, not at one point the values of higher order derivatives, rather we need the function value at different points. So, we will naturally come up with some other polynomial, not the Taylor's polynomial, which also does the purpose of approximating a complicated function by a polynomial. So, for ordinary computation purposes, it is more efficient to use methods that include information at various points, not at just particular point, because in many applications, many experimental results we have at different points the given data, and then we want to know that which polynomial fits the best the given data points. So, the first question is whether given data points the polynomial which we want to fit, is it unique, and does it always possible to construct such a polynomial. So, for n plus 1 data points, there is one and only one polynomial of degree less than or equal to n that passes through all the points. That is what we are going to prove here in this result. So, that is the main result, that there it exists and it is unique. So, when n plus 1 data points are given, there is only one and only one polynomial of degree this less than or equal to n that passes through all the points. A very simple example which we can talk about, that when we are talking about the 2 points and we know that there is a unique straight line. So, a polynomial of degree 1 which passes through these given 2 points, there cannot be two different lines which passes through both the points. So, it is a uniqueness and there will be always a line. So, there is existence. So, there is only one straight line, a first order polynomial in this case when 2 data points are given, that passes through the given 2 points. So, now to prove this result, which is true for a general n, we will consider a second order polynomial. We will prove this for a second order polynomial, and one can extend this for nth degree or order polynomial. So, suppose our function here with the polynomial a naught, a 1 x, a 2 x square, a second order polynomial. We have here. So, how many unknowns do we have? We have a naught unknown, a 1 and a 2. So, there are three unknowns which will define this polynomial. So, in order to compute these three unknowns, we basically need three data points. The point is a straightforward method for computing the coefficients of the polynomial of degree n. So, if we talk in general n, based on the fact that n plus 1 data points are required, like in this case it is a second degree polynomial and we need 3 data points, because there are 3 unknowns, and for each data points we can construct one linear equation in a 0, a 1, a 2. So, we need 3 data points to have 3 equations, and they can be solved, and we will see in this particular case that there exists a unique solution. So, for this uniqueness we need n plus 1 data points and 3 data points in this example to determine n plus 1 unknowns, and in this example we have 3 unknowns for instance. So, now this is the polynomial to be fitted with the given data, and suppose there are the 3 data points x naught f x naught, x 1 f x 1 and x 2 f x 2. So, these 3 data points are given and we want to construct a polynomial which actually passes through these 3 points. So, if the given polynomial passes through the given data points, then it must satisfy, that means the f x 0, if we pass here the x naught point. So, f x naught must be equal to a naught plus a 1 x naught plus a 2 x naught square. So, that is the first condition we should have, that this polynomial should satisfy the given data point. The second data point is x 1 f x 1. So, when we substitute in the polynomial x 1 for x, then we should get f x 1, and the third one, when we substitute this x 2, we should get f x 2. So, these are the 3 equations we have from this given polynomial which passes through the 3 given points. This we can also rewrite in a matrix vector form. So, here the matrix is then the coefficient of a naught, that is 1 here, the coefficient of a 1, that is x naught, the coefficient of a 2, that is x naught square. Similarly, here we have the coefficient of this a naught, that is 1. So, it is not 2, it is 1, and then we have x 1 there, we have x 1 square, and in this case again we have 1, we have x 2 and we have x 2 square. So, this is the system we have for corresponding to this given linear equations. So, having this system now, what we will analyze now, that this system of equations has a unique solution. This we will show now in a minute, and when we compute the determinant of this function here, what we will realize that the value of the determinant is nothing but x naught minus x 1, x 1 minus x 2 and x 2 minus x 0. So, having this value, what we realize that if these points x 0, x 1, x 2 are different, if these points are different, what will happen, that the value here will be non-zero. So, the value of this will be non-zero, and once we have this determinant non-zero, we know that there will be a unique solution. So, if these are distinct, and they are obviously distinct, we are talking about x naught, x 1, x 2, they are distinct points, then definitely we have this unique solution. So, in practice, what is the problem now? So, this is what we can this explains the method, also the way we can construct a polynomial given data points. So, if n plus 1 data points are given, we can construct uniquely a polynomial of degree n. So, what is the problem? Why we are now discussing more about the polynomial? The reason is that in practice it is observed that the above system of equations is ill conditioned. What do we mean by ill conditioned here? So, when whether they are solved, so the system or the equations, they are solved with an elimination method like Gauss elimination etc., or more they like iterative methods we have already discussed. So, any other efficient algorithm we take, the resulting coefficient can be highly inaccurate. So, this ill condition means very little error in the in this matrix entries can lead to a very inaccurate, highly inaccurate values of its solution, that means A naught, A1 and A2. So, that means the ill condition. So, this is what observed. We are not going much into the detail of this part, but for large n one can understand that this system is actually difficult to solve because of this ill conditioned system. So, what we have then, there are some mathematical formats which we will be talking about in the next lecture, and those are the methods how to get this interpolating polynomial without following this approach, that constructing the system of linear equations and then solving them. Rather, we have a better ways and direct ways of constructing the polynomial without solving such a system of linear equations. Well, so the last portion of this lecture will be talking about the error in the interpolating polynomials, because the polynomial is unique, and now we can talk about, before we go for different methods how to construct that polynomial, because the polynomial is unique. So, we can talk about what is actually the error in this approximation. That is also an important point which we should address. So, suppose x naught, x1, x2, x3, xn, these are n plus 1 points, and we let that x be a point belonging to the domain of a given function. So, all these points x0, x1, x2 etc., and also we have taken one more point x, these all belongs to the domain of the function. And we assume that f is n plus 1 times differentiable function, where this I x is the domain here, or the interval containing all these nodes, and this x is the smallest interval we can think of, which contains all these points including this x. So, I x is basically the domain of this function f. So, then the interpolation error at the point x. So, because we are talking about the polynomial which or the function which has its domain. So, at any point x, difference between the polynomial and the function is given by, so f x minus this p n x, one can compute by this formula here, which has this n plus 1th order derivative. So, f the n plus 1th order derivative at some point xi, which belongs to this interval itself, factorial n plus 1, and there is a product here x minus x naught, x minus x1, x minus x n. So, this is the error we have when we interpolate this function, or approximate this function by the polynomial taking these n plus 1 points. So, we want to derive now how to get this formula here for the error. So, the proof we will just go for the outline. So, the result is obviously true when x coincide with the any of the interpolating nodes. Why? So, if we are talking about that this x coincide with the x I, so then we have here x I, and this is also x I, and naturally this polynomial passes through all these points f x I. So, this will be 0 here. So, then the error is 0, and then here this side also this formula will give, because when x is one of these nodes. So, this will make everything 0. So, we have 0 equal to 0. So, that is obviously true when this x coincide with the interpolating nodes, meaning this x naught, x1, x2, x3 and so on. And now, for simplicity we assume, because there was a product here, a lengthy product, x minus x naught, x minus x1, x minus x n. So, this product here we are denoting with the w n plus 1, n plus 1 is actually the degree of this polynomial again, because this product is nothing but a polynomial, and the degree of this polynomial is n plus 1. So, we are denoting this by w n plus 1. And now, we define that for any x we take in the domain of this function, where we want to calculate this difference between the two, we define this function, and this function will help us to prove exactly this formula for the error, which is the aim of this lecture now. So, we define this function g t as E n t, E n is defined already, that is the difference between this f x and the polynomial p x. So, here we have E n t, then we use here this w n t, which is already defined here as w n x. We have again E n and we have again w n. So, in terms of this E n and w n, which is also w n is defined here and E n is defined there. So, in terms of these w n E n, we have defined a function g t, and now we will discuss what are the properties of this g t and how we can get out of, with the help of this function, the error formula. So, the first thing we should notice that since this f is n plus 1 times differentiable function, this g is also n plus 1 times differentiable function, and why? Because g t is nothing but the E t, E n t and w n plus 1 t. E n x and this w n x, they are constants, because for any but fixed x here we are talking about this formula. Here t is only the variable which we are considering now. So, what is E n t? E n t is f t minus this p n t. So, again this is a polynomial and f is a n plus 1th time differentiable function. So, E n we have here the n plus 1 time differentiable. So, there is no problem for the differentiability of this E n for this g t as long as this first term is concerned, and the second one here, this is polynomial, these are some fixed values. So, this is fixed for given x, and w n t is a polynomial. So, here we have this polynomial, here we have that function which is again n plus 1 time differentiable. So, everything here we can differentiate n plus 1 times, that means the g function is n plus 1 times differentiable. That is the first property of this function g. So, having this g, we have E n, we have w n already, and what we will notice now that this g t, this function has n plus 2 distinct zeros in this I x. How this function has n plus 2 distinct zeros, we will notice now. So, just consider that g x I. So, we have E n x I, we have here also w n plus 1 x I. Now, this w n plus 1 x I, this is the w n plus 1. When we put here for x equal to x I, this will become 0. So, this part is 0 and hence this part is 0. So, the second part is 0. Now, coming to the first one, when E n x I, this error here at x I, naturally that will be also 0, because this x I is the nodal point. So, this is also 0, and 0 minus 0, then everything is 0 here for all I 0, 1, 2, 3 and so on n. So, there are here n plus 1 points. So, here we have n plus 1 points where this g x I vanishes, g vanishes. So, there are n plus 1 distinct points we have discussed, and the one more point, that is the x, which we have already fixed at the beginning. It is arbitrary point, but fixed point here. So, this at g x also we will notice that this is equal to 0, because we have now E n x, w n n and so on, this two are the same. So, cancel out, we have E n x minus E n x, and that is 0. So, here the g x is also 0. So, we have n plus 1 points here, n plus 1 and plus 1. So, the total, there are n plus 2 distinct zeros in I x of this g. So, having this property now, we can use the Rowe's theorem, which will say that g prime, its derivative, will have at least n plus 1 distinct points, because whenever we have a function, for instance, it has these two zeros here. So, if f a is 0 and f b is 0, then the Rowe's theorem says that there will be a point in between where its derivative will be also 0. So, between the two zeros here, its derivative will have 1 zeros, and the same argument we can have here. So, the g function g is 0 at x 0 and x 1, x 2 and so on, and also x n, and also there is a point x somewhere. So, there are n plus 2 points there, and between each these two zeros there will be one point where g prime will be 0 and so on, and when we count this will be just one less than the number of these zeros. So, there were n plus 2 zeros. So, g prime will have n plus 2 minus 1, that is n plus 1 distinct zeros. By recursion, we can continue this process that g double prime will have n distinct zeros and so on, or ith derivative of this g, this is ith derivative of g, it will admit n plus 2 and minus the here if it is jth. So, let us say the jth derivative, then n plus 2 minus jth distinct zeros this will have. So, n plus, now we are continuing, and now let us say if j is n plus 1. So, if we put here n plus 1, so this will remain just 1 there. So, g n plus 1 will have at least 1 zeros, this is the implication of this Rowe's theorem now, and which denotes, so we are denoting here by this xi, this n plus the g n plus 1th derivative has 1 0, and that is we are considering that this is at xi. That means that g n plus 1 xi equal to 0. So, this result we have. So, what do we have? We have g n plus 1 xi equal to 0, w n plus 1 was defined by this product, and we have this function which we have started with. Now, we can talk about the n plus 1th derivative of this, that is E n plus 1th derivative, and the n plus 1 derivative of this w t, the rest here they are just fixed values. Now, we should note that talking about this E n, so E n t was f t minus p n t, and we take the nth order derivative. So, that nth order derivative will go to f, and this is a n degree polynomial, n plus 1th degree n plus 1th derivative will be 0 of this polynomial. So, what we have that E n, the n plus 1th derivative will be simply the n plus 1th derivative of f, because this is equal to 0. What else we have? The n plus 1th derivative here of this w, w is again this n plus 1th degree polynomial. So, here we have something x n plus 1 plus anything else there with lower degree terms, and when we take the n plus 1th order derivative, so simply we will get n plus 1 factorial, which is written here. So, that is done, and obviously, we have this result that n plus 1th derivative of g at xi is equal to 0. So, having all this result now, we will substitute here for t is equal to xi. So, if we put here t equal to xi, what will happen? G n plus 1 at xi will become 0. Then here we have this n plus 1th derivative of E, that is nothing but the n plus 1th derivative of f. So, we have here f n plus 1 xi, and then here also this n plus 1 factorial, then we have here E n plus 1 over w n plus 1. So, this is what we have now from this given function which we have chosen, and now just from this we can conclude that E n x. So, this is E n x will be equal to this one, and this is exactly the error formula which we want to derive. So, now in this lecture we have also derived the error formula, because this polynomial is unique. So, irrespective of how do we calculate, but we know that what will be the error. So, these are the references we have used for preparing this lecture, and just to conclude that we have introduced the polynomial interpolation, which is the method of determining polynomial that fits a given set of data points, and we have also proved the existence and the uniqueness. So, for n plus 1 data points, there is one and only one polynomial of order less than equal to n. Why less than equal to n we are talking about? Because for instance, if we take 3 points, so according to our discussion we should have a polynomial of degree 2, but in this particular case, because they are points in one line, so we will get only the linear equation, that means only the line, because they were in one line, collinear points. So therefore, so here again having the 3 points, but we are getting a polynomial of degree 1. So that is what we have written here, that it is always possible that when n plus 1 data points are given, there is a one and only one. So uniqueness is always there, and there will be a polynomial of degree less than or equal to n that passes through all the points. And we have also discussed the error in the interpolating polynomial, which is given by this formula f n plus 1 at some points I, and then we have n plus 1 at factorial, and this product x minus x naught, x minus x 1 and x minus x n. So, that is all for this lecture, and I thank you very much for your attention.